Okay, so now we're going to put quantifiers together. Okay, so we can have multiple quantifiers on a proposition. So we can have it quantified by an existential or two existential quantifiers, or an existential and a universal quantifier. And that happens if you have more than one variable. Okay, so in general, multiple universal quantifiers can be a range of any order. So if you just have like a bunch of universal quantifiers, it doesn't matter which one you put first. Multiple existential quantifiers can also be arranged in any order. But order is going to matter if you have existential and universal quantifiers together, if they're mixed. Okay, so if you're going to mix where you place them, it's going to change the meaning. All right, so let's look at some combined statements here, multiple quantifiers. So let's say I have a proposition P that's dependent on x and y, has two variables. So we have two universal quantifiers together. It doesn't matter whether you put for all x or for all y at the beginning or the end. It doesn't matter if you mix them. Okay, so this means that the statement propositions pxy is true for every pair xy, right? And it's going to be false if there is a pair of values xy for which pxy is false. Right? If I mix a universal and existential, then the order is going to matter. It's going to have a different meaning depending which one comes first. So for this case right here, it says that for every x, there exists a y for which pxy is true. Right? And it's going to be false if there is an x such that p of xy is false for every y. Okay, so you're sort of negating both the universal and the existential. All right, now if I put them in the other order with the existential first, this says that there is an x for which p of xy is true for every y. Now if I negate it, that says for every y there is an x for which p of xy is false. All right. Now, existentials together, the order doesn't matter. So there exists an x, there exists a y, you can switch order, they'll have the same meaning. So this says that there is a pair xy for which p of xy is true. And if I negate it, then it says that pxy is false for every pair xy. All right, so let's look at example 11. Let's translate these right here. Okay, so I have two universal quantifiers. Again, it doesn't matter which order I put them in, but we can refer to the chart that says that this statement is true for every pair xy. So x plus y equals y plus x for every xy pair. If I have two numbers, this statement is true for any two xy numbers. Okay, let's look at B. So this one, the universal comes first and then the existential. So this says for every x, there is a y such that is true. Okay, so x plus y is y plus x. Let's do this again. And so for every x, there is a y such that x plus y equals y plus x. All right. Let's look at C. Okay, so this has three quantifiers to it, two universal, one existential. Okay, so this one we can translate as for every pair xy, there exists a z such that x plus y equals z. Okay, and let's look at D. So D is basically C switched around. So this says that there is a Z, there's a value of Z for which the statement x plus y equals Z is true for every xy pair. Okay, right, so these are the translations here. All right, so let's try these translations. Okay, so we have the sum of two positive integers is always positive. Okay, so we see that we have two variables, two positive integers. So we can say for an always, kind of implies that we're going to look at the universal quantifier. So I'm going to say for so I'm going to write for all x and for all y. Okay. There are two positive integers. So actually, let me say for all x bigger than 0 and for all y bigger than 0, because we can sort of have specify our restrictions or our universe here, then the sum of the two integers is positive. So these are my variables, and we can sort of specify the domain restriction, the universe restriction, that they're positive, and this is my p of xy right here. So p of xy is the statement that x plus y, the sum is bigger than 0. All right. Now let's look at B. So every real number except 0 has a multiplicative inverse. Okay, so every real number, so for all real numbers except 0, for all x not equal to 0, then I need a statement that says that it has a multiplicative inverse. So there's going to exist a y such that x times y equals to 1, right? So for all x not equal to 0, you're going to have another value. There exists a y, and this is their multiplicative inverses. Multiplicative inverses, the reciprocal. If you multiply them together, then you're going to get 1. All right. Okay, so let's look at C. So if a person is a female and is a parent. Okay, so let me define some things. So F is female and P is parent. X is female, X is a parent. And then this person is someone's mother. So mother has to be two variables, like X is the mother of Y. All right. So let's see. If a person is a female and is a parent, then this person is someone's mother. Okay? So we're going to say for all x, which are females and parents, then there's going to exist a y such that x is the mother of y. Okay, so for any people that are both female in parents, then there's going to exist a y, which is the child, right? So y is such that m xy. Xy means that x is the mother of y. We can also write it as this, put the quantifiers together. So for all x, there exists a y, such that if x is a female and a parent, then x is the mother of y. All right, cool. Okay, so let's look at translating this statement. So we're going to use quantifier to express the statement that there does not exist a woman who has taken a flight on every airline in the world. All right. So let's start with, let's leave the not out for now. Okay, so let's translate there exists a woman who has taken a flight on every airline in the world. Okay, so let's see what variables we have in here. So we have variables we can call W is women. Okay, so our W is the women, or the woman that I'm interested in out of all the women. Okay, and we have A is airlines, and we have F is a flight. Okay, so these are my X, Y, Z. I have my variables here. All right, so we can also see that we're going to have some compound statements, okay? Because like the woman takes flights, and the flights happen on airlines. So for example, let's say I'm going to call, maybe not A, it's P. So PWF would be the statement, the woman has taken a particular flight. So W takes flight F, right? And let's have RFA to be the statement that the flight is on airline A. F, flight F is on airline A. Okay, so now we're going to say that there exists a woman. There exists a woman such that for every airline A, there exists a flight such that PWF, the woman was on that flight, and RFA, the flight happened on that airline. Okay, so that's the translation of that statement. But we don't want that statement, we want the negation. Okay, there does not exist a woman. Okay, so we're going to do the negation. So we want the negation of this. Okay, so the negation basically propagates from one quantifier to the next, and it changes it. So when I negate the existential, it's going to be every woman. When I negate every airline, there exists an airline. When I negate there exists a flight every flight. And the negation goes to the combined statement here. All right, so the negation changes the universals to existentials and the existentials to universals. But then with De Morgan's law, I can distribute the negative here. So I have, for every woman, there exists an airline whose every flight there was not a woman on that flight, or there was not on a flight on that airline. So that's how the negation works its way in. So the negation of there exists a woman who has taken a flight on every airline in the world can be translated as, for every woman, there is an airline for which every flight, either the woman was not on that flight or the flight was not on that airline. All right, I know, a bit confusing. Okay, so let's stop here.